Hey there, everybody. Thank you so much for joining us for our gas laws webinar today. We are so excited to dive in with you all. As folks kind of get situated and get set up, I do just want to send you to your Zoom window and have you navigate to the bottom of the Zoom window. You'll see what looks like a little chat bubble. That chat bubble is how we will be communicating today. So I would love to encourage you to go ahead and click that chat bubble. When it pops up, it'll say webinar chat at the top, and then it'll have like a little to section. And I believe the default on that to section is to hosts and panelists. That'll send a message directly to us. However, we don't want to look like we're talking to ourselves during today's presentation. So we ask that when you send us questions, please actually set that to everyone. You never know what other educators in the room are wondering. We can all share that information. So please make sure when you drop questions, comments, etc. into the chat, make sure that to is set to everyone. And in an effort to practice this, Noose and I were just talking about the new movie. What is it called? Noose
Thunderbolt.
Thunderbolts. Yes. Have you
Well,
all seen Thunderbolts? What did you think? No, Melissa, I haven't seen it
I
either.
haven't.
I haven't either, but it's an OMSI, so I'm tempted.
Might as well. Yeah, OMSI, for those of you who aren't in the know, is the Oregon Museum of Science. What's the
In
I?
industry.
Industry. Yeah,
Industry.
that's
Yeah.
weird.
Yeah. And Noose volunteers there often. And so that's why we were kind of chatting about that. So let's see. We have some comments in the chat. Have not
Oh, nobody's seen
seen.
it.
Yep. Haven't. No, but saw Sinners. I enjoyed that one. Have not seen it. Yeah, I don't know. I didn't see it either. So I'm glad we're all
I don't know if that's
behind
good
the
or
zeitgeist.
bad.
I feel like
Right.
the Marvel movies have kind of lost some of their
Yeah, I kind of feel it.
uh opening weekend. Gotta rush.
Yep.
Wait, they show up on Disney Plus, so it's like
There.
you need to
Yep.
pay the money to go see them. Yeah. Yeah, OMSI was just voted one of the best museums in the country, science museums in the country, and they have a chemistry lab. So hey, Arrow, and so I volunteer in the chemistry lab on the weekends, and it's a lot of fun. Boy, every age, name the age, 390, and it's always fun. So wow, 24 people, yay.
Yeah.
Yep. I've been
Well,
taking my
maybe we'll.
daughter since before she was 2, so it's a great school or great museum.
That's
Yeah,
awesome.
they do spend a lot of effort to try to have something for everybody to do. So
Yeah.
it really, if you're in Portland, you got to see housing.
Hmm.
Well, tell me when you want to start because I want to squeeze 4 gas laws in an hour.
Yeah, that's what I'm kind of thinking. Let's hop to housekeeping items. If you hit the
Okay.
next tab,
Whoops, I'm on the wrong screen. There we go.
perfect. Awesome. Will, no, you don't have to sign into Zoom Workspace. You should be able to just watch along, so you are good to go. Um, First item of my housekeeping, you will receive a recording of today's webinar. It usually takes us about 3 to 5 business days just to edit it and get it uploaded, but as soon as it's ready, it'll be both on our YouTube and our website. And once we upload it, we're going to email it out to you, so keep an eye on your inbox. In that follow-up email, you're also going to receive a link to a resources folder that has experiment files, today's presentation for you to click along, and a certificate of attendance. I'm going to drop a link to that resources folder in the chat as soon as I'm done talking, so keep an eye out for it there. And we would love to answer your questions during today's webinar, so please drop your question in the chat if you have something, and we'll try to get to it. If we happen to just miss your question or you think of one later, please reach out to us. You can reach us at chemistry@vernier.com. All that being said, thank you so much for joining us, and I will pass you off to today's wonderful presenters. And stick around, we are doing a giveaway for everyone online at the end of the webinar, so stay tuned.
Pretty good giveaway too. So just a little stick there. Yeah, hi guys. This is I'm Deuce, Hisim, and my other department colleague, Melissa. She's going to try to, oh, she's not going to try, she's going to do it, answer questions while I'm trying to zoom through 4 gas laws. Melissa, did you want to say anything?
Nope, just what you said there. Make sure you put them into chat. Any questions you have, put them into chat. If I need to interrupt Noose, I will, or I'll just answer in the chat. And again, make sure it's set to everyone. And yeah, let's get
All
to
right,
gas
let's see.
laws.
And then just a quick, anytime you need help, folks, please don't hesitate. We have all kinds of ways that you can converse with us, and during the session, but also if you're doing any experiment, chemistry wise, we're the best at chemistry. I did teach some physics, but I'm not as strong. Definitely trying to learn more about chemistry as I work here. Um, Here's what we're going to do today, and I'm kind of pushing this a little bit because I'm going to try to squeeze them all in an hour, and it's going to be a challenge. But I think everybody does Boyle's Law, so I'm going to put that to the end, and I'm going to do the one that's probably the most challenging first, and that's going to be Charles' Law. Don Volz wrote a Don and Jack wrote a very creative way to do this, and I'm going to share that with you today. And we'll try to get an absolute value for an absolute zero value too. So we'll see how that goes, and we'll do that with the Gay-Lussac's law as well. We'll see about the other two. Yeah, Avogadro is another fun one, and like I said, a lot of people have done Boyle's law. So if I don't get to it, I apologize if that's the one you were hoping to see. Um, these are the setups, and actually you're going to see them live here in a second anyway. But if you go and get the presentation, you'll have the pictures of the setups. I'm going to use the go direct pressure and temp today for 2 experiments. Pressure for all of them, temp for 2. But you could do this with LabQuest sensors. So don't feel like if you have the wired, sensors with the white plugs, you can't do this experiment. You absolutely can do it with graphical analysis, almost identical to the way I'm going to do it today. So let's collect some data. Look at that. Mo wants to do some chemistry, so let's do that. Um, First experiment. Um, Charles law. Okay, so in Charles law, the volume is not going to be constant because we're going to be looking at volume versus temperature. And we're going to be measuring the volume in this Erlenmeyer flask. And the thing that might surprise some of your students is the fact that, it says 125 on there. Isn't it 125 milliliters? Well, of course not. And so that volume that's listed under there, I shared that with Dylan earlier, 148.93. Hang on to that number because we're going to need it in just a few minutes. And Dylan's going to crank up the calculator and help me when I need a total volume. So we're going to get to that. Let's go ahead and do the experiment. So there we go. So I apologize. I set this up partially in advance because time being what it is. However, you'll notice that if you look at the graphs, they're against time. We don't want that. We want to be able to record the pressure of, pardon me, said that wrong. We want the pressure to remain constant. So that's why we're looking at the pressure, but we want to record the volume and the temperature. That's what we want to do. So I've got a very cold water bath here with some salt in it. And temperature probe is sticking in there. And, my classroom, I could get those things down closer to 10, -10, but I think you'll get the point. What I need to do is change the mode of data collection. It's collecting against time, not good for us. We need to change the mode, bottom left corner of graphical analysis. Click there, and we'll change the mode from time-based to event-based. Now, for the sake of Charles' law, the event is going to be the total volume of the gas. Okay. And we'll look at how I'm going to get that in a minute. And if you're a purist, you'll put cc's here, and if you're not a purist, you'll put milliliters. I don't care, but when I was teaching, it was always cc's. So anyway, that's good. Let's go ahead and hit done, and let's take a look at the graph now. We have temperature against volume. Most people, when you do Charles law, it's the other way. So I'm going to switch it to the other way. The temperature is going to be the independent variable. The volume is going to be the dependent variable. So I'm going to switch them the other way. Let me do it that way. And one other thing to be aware of is that your gas laws, we can do it in Celsius. We can always convert that to absolute temperature. Or in graphical analysis, if you tap the meters, you can change to whatever unit you want. Like if I want this to be in Kelvin, I can do that. Same with pressure. I'm going to leave it in kPa, but if you like doing stuff in torr or millimeters of mercury or something like that, you can always switch it. I'm not going to do that though. So what I'm going to do is I'm going to take this flask and I'm going to close the valve for the moment. And I'm going to lower it into that very cold water bath. And I want you to notice how I'm holding the flask. I'm actually holding it from the syringe so I can get the whole volume of flask into that water bath. Notice my expensive water baths. I mean, I don't know about you guys, but how many 1 liter or 2 liter beakers could you afford? My budget was pretty tight. And so being able to afford a classroom set of beakers was definitely kind of a hard thing. So 2 liter bottles are wonderful. I'm going to start collecting data. Nothing's going to happen. And what it's doing is I'm watching the meters and I'm waiting for the pressure and temperature to stabilize. Now, for the sake of our 1 hour workshop, I am going to speed things up a little bit. But technically, you should probably wait, a few minutes and make sure everything is stable. And then what I'm going to do is I'm going to tap keep. And what am I going to type in there? Well, I'm going to type that value, which I've totally forgotten. Dylan, 148 point what?
148.93.
93. Okay. Now, how did we do that? Well, I did put the picture in the presentation of how we did that. Let your students figure it out, right? Let me go back to the present. I should tell you what. I'll switch this to another water bath. Then we'll look at the presentation. So let me raise this up here a little bit. The other thing we need to take note of is that pressure. So we'll need to take note of that, and we'll look at that in a minute. So I'm going to switch to, instead of a really cold water bath, I'm going to switch to a cold water bath. This is one that it's better to do cold to hot. Okay, it's better to do it that way than to try to jump around. Okay, so I'm going to put this in the water bath. Notice how I'm holding the flask again. So the whole thing gets in the water bath. While that's equilibrating a little bit, let me go to the slideshow because I want to show you this. I made this up. I don't know. Jack and I talked about this a long time ago, and the idea was to give the kids a chance to kind of work out how am I going to figure out the volume of the flask, right? Well, it's not really just the volume of the flask, it's the volume of the gas that's being tracked. So it's not just the flask, there's also gas in this lure lock connector at the top. So there's a lot of things here you don't need. But the idea is, I let the kids come up with a method and have them explain to you how they got that volume. And so what I did yesterday is I weighed not I weighed that flask with nothing in it, just this setup, but with nothing in it. So and I did use the correct stopper. This is a number 5 1 hole, but yesterday I used a number 5 2 hole, and I filled it with water and I weighed it again. Okay, so that's where that 198, 148.93 came from that Dylan. And now the other thing we need to pay attention to is the pressure. Look at the pressure. Then what with Charles law, the pressure needs to be constant. So we need to adjust the volume because this thing is warmed up now and the pressure's gone up a little bit, another gas law. We need to adjust the volume so that the pressure is 94.6. So let me pull this up a little bit. So this is why you want to start cold and work your way hot because you'll run out of syringe. 94.7. So remember, we want to keep the pressure constant. All right, that's not bad. I mean, I think I'm gonna be goofing around too much. I'm gonna close the valve. Okay. I'm gonna call this good, even though it may or may not be equilibrated. And so now we need to calculate the volume because it's gonna come up and say, what's the volume? Well, it's gonna be, Dylan, you ready? 148.93 plus, I'm reading on the syringe, 5, 6, 7, 8. It looks like it's right on 8 milliliters. So plus 8. Dylan, what is that? What's that sum?
It's 156.93.
All right. Keep that point. Let's go to another water bath. Let's raise this thing up. Isn't this clever? Think about it. You know, when I first started teaching, how did we do Charles Law? All right, don't yell at me. Don't be mad. I mean, mercury in tubes, right? That was what we were doing way back in the day. Um, and so, this is kind of neat, because everything you see here came with the pressure sensor. I'm using a electrode support to hold the temperature probe, but you could use a clamp. And so, it's pretty straightforward setup. And this, these 2 liter bottles are, you recycle them. So you're going to have plenty of those. All right. Adjust the pressure. What was the original pressure? 94.6. So we need to open the valve and then gently pull the syringe up. 94.6. Yeah, close. That's pretty close. I'm going to call that good. So, Dylan, 148 point, whatever the heck that was. Okay, 148.93 plus 11.4.
All right, that's 160.33.
160.33. All right, let's keep that point. Let's see if we can squeeze another one in. Sometimes the hot one will shoot the syringe out. And so you don't want to make this too hot. We'll see. If it does, I'm going to have to stop, but we'll give it a shot here. It'd be nice to have 4 points instead of just three, but three is better than two because two will definitely give us a straight line. We'll have to see how good my work is by checking my absolute zero value. So get the thermometer in there. And it's also possible that the stopper will pop out. And if we lose that point, oh well, we've got the other three. So let it warm up. Okay. And the object is to keep that pressure constant, right? So I need to get that adjusted. Hopefully, the other possibility is if you don't pop the syringe, but it's going up above the syringe. These syringes, we do 20 milliliter syringes, but any syringe with a lure lock connector will work. So, you could potentially go get a larger syringe. But anyway, let's see, 94.6. So let's see if looks like I might just barely sneak it in. 94.6. Oh man, it's so close. 94.8. And I'm right at 20. Wow, now I don't know. It hasn't warmed up all the way either. So I'm probably cheating here a little bit, but I'm going to call it good. Okay. So Dylan, 148.93 plus, let's say 20.1.
All right, that's 169.03.
All right. You're off the hook, Dylan. You're done. All
Thanks,
right.
News.
Let's see how good it came out. Okay. I think this is still warming up, so I'm not 100% sure. But anyway, we'll stop collecting data. Let's see how good it is. We'll do a curve fit. This one should be somewhat linear. Looks like I got almost 3 nines correlation, so not horribly bad. Let's switch the axes. So if you're doing, PV equals nRT and you're trying to get a constant for V proportional to T, then the slope will be the constant, right? So, but if you're trying to get an absolute zero value, which my students were of course trying to do, let me switch this over to volume and temperature, and let's look at that y-intercept. So let me do a curve fit, and let's see, what's my y-intercept? -16 out of 273. That's better than 10%, right? That's kind of like 6 or 7% error. So that's not horrible, No, the y-intercept should be zero if it's, you guys know that. So anyway, one law done. Let me go save this. Anybody have any questions while I'm doing this? I think, for Charles Law, whoa, baby. Okay. What a nice way to do it, and no mercury involved. Back in the day, I remember sticking mercury in capillary tubes and trying to measure the diameter and trying to measure the volume. And that's what we did. All right. Law two. Law two is, what are we doing? Gay-Lussac, so pressure and temperature. What reason I want you to see this is because it uses a different mode of data collection. So I'm going to start a new experiment. I saved that last one because it wasn't horrible. It should remember my sensors so that you can kind of see them in the background there. So I shouldn't have to like add any sensors or anything. But what's happening in this one, and let me go ahead and get this cooled back down because that thing was sitting in that hot water. I'm going to also put the syringe back where it was to start with. Because in this one, we don't move the syringe. The volume is constant, so the volume is going to be 148 point whatever. But let me go ahead and put this all in the cold water so it can equilibrate while I'm talking. Data collection. Now notice I started a new experiment and it says time. No good. We want pressure and temperature. So we're going to take the data right from the two sensors and we're going to plot them against each other. So we're going to use events with entry again, bottom left corner. All this is, of course, in the lab write-ups. And by the way, there's different ones of these experiments in the advanced chemistry book. There's one experiment called gas laws that's all of these. And then in food and in forensics, I put other ones, and I don't remember which one is which in which book. But anyway, getting back to this, we're going to use selected events. What that means is that as soon as I hit keep, it's going to grab a value. That's it. Okay, so I don't have to enter anything because the volume is constant. I don't have to do anything with the volume. I just want to know at different temperatures, what's the pressure. So I'm going to hit done. Let me get the meters up here so we can see things better. Okay, and that water bath, I know I can do better than that. Let me see if that salt, I guess we're running low on actual ice in there, but that's okay. Let me raise this up a hair bit. I like having the whole thing in the water bath, but the way the water goes is actually warmer towards the bottom. But anyway, all right, start collecting data. This one's faster because all I need to do, oh, degree C. All right, we'll leave it that way and we'll look at the y-intercept. It'll be in C, so that'll be okay. So once these meters have stabilized, hit keep and Shazam, there's a point and it's right on the graph. Okay, events, not events, temperature. Okay, pressure. There we go. Hey, look at that. I've had numerous people this week call and say, how do I change the axes? You just click on them. It's really that easy. Okay, all right, new water bag. So let's move this along here. Where are we at? Almost halfway through. This one's gonna go pretty quick. Unless I screw something up, which is not beyond me. So I brought some towels in here just in case. All right, in the cold water bath, not negative. This is more like in the single digits water bath. So what you got to do is you got to watch the meters. I like these big ones, and so when you're using graphical analysis, if you click on this little window of windows, box of boxes, you can turn the big meters on. I mean, the little ones down here are okay, but my eyes are old. So what the idea is, wait until things level out. Okay, stabilize is the right word. And then click keep, and it will just plot those points. Shazam, there's two. All right, let's go. I'm going too fast. Okay, I want to get this done. So, because I want to show you Avogadro. If you haven't seen that one, that's a pretty slick one. I used to do that for years, before there was an actual write-up of a lab. Once again, Jack had it in advanced chem, so you could argue it's been there since like the late 90s. But I don't know how many people did that experiment. I did, but it's an experiment called gas laws in advanced chemistry with Vernier. All right, let the temperature and pressure stabilize. Some people have said, what about putting the temperature probe inside the flask? I have not gotten better data doing that. It certainly would make sense. Put like a surface temperature probe and figure out a way to seal it in there. I've tried some different things like that, and I have not gotten that considerably better data. And the whole point is for kids to see this relationship, and so it doesn't bother me that much that it's maybe a little off. I'll keep that value. And one more, doesn't look too horribly nonlinear, even though I'm going pretty quick. This one's kind of nice, right? And now in my classroom, I had six peninsulas with lab stations on opposite sides. So if you set up the water baths, if you set up six sets of water baths in your classroom, in your lab, kids could share them, and that wouldn't be too bad. And then you've got, it's like I said, it's 2 liter bottles, unless you've got, plenty of flasks, or pardon me, beakers. All right, that's the warm one. Let's see if it pops. Hopefully not. Like I said, don't overdo it with the warm water bath. If you do, it's going to pop and you're not going to get that point. So, you might fiddle around and find the highest temperature that won't pop for you and maybe go 5 degrees below that. And then try to get a few more points. I mean, you could fiddle with ice and water and probably get a few points. But if you overdo it, it's just going to pop and you'll lose that point. So that's close. I'm going to call it good. Keep that value. Let's stop. How linear is this? Let's find out. So I'm going to do a quick curve fit on here. Let's see how linear it is. Oh my God. Now you saw me. I didn't cheat. Look at that correlation coefficient. That means that the points are as close to a line as they can be. The one is the best value you can get. Now, of course, the proof to the pudding will be, what's my y-intercept. So we'll switch the axes and check. But P equals 0.3259 kilopascals per degree times temperature. Oh, yeah, it's in degrees C. You should probably change it to degrees Kelvin, which you can do on the fly. But I want to leave it this way just so that we can see the absolute value, absolute temperature in Celsius. But you could do it on the fly, and it'll fix everything. It'll automatically adjust everything. So it's kind of slick. Negative 292. That's off by less than 10 degrees out of 273. So that's less than 5% error. You're trying to find a value for, and a unit of nature. Did I get this all done in half an hour? Yeah, isn't that great, Elvira? I mean, I honestly, you saw me do it. I didn't cheat. I want you to challenge your students. I saw the Vernier guy get a correlation of 1. See if you can do it. I saw the Vernier guy get under 5% error. See if you can do it. Melissa, what's going on?
Oh, there came up a few questions that I thought I'd have you answer directly. And one that I thought was really good, because I think you've been experimenting with one of these, but do you have a lab that can use long gas tubes?
Use what?
Long gas tubes. Like, so I guess just a longer version of that tube to measure different things. And I know you did like some density.
Well, the long one, there was, I used, are you referring to Dalton's law and looking at ammonia and hydrogen chloride? I mean,
There weren't specifics, so Elvira, if you want to add more to
not
the your
Dalton's law.
questions.
I'm,
I was thinking of the density one you were doing, but maybe
yeah,
they meant
I said
something
that
else.
wrong. It's not Dalton's law. It's, what's the law where you compare the rates at which the gases diffuse through a hole? I can't think of the law. Come on, somebody knows that. Yeah, thank you. Graham's law. Good stuff. Yeah, that's the only one that I use long tubes for. So I don't know if I can think of a capillary tube. I don't know how you would use, I mean, so back in the day, the reason I mentioned the capillary tube earlier is because I used to put mercury in I mean, yeah, ignorance. I used to put mercury in the tubes and then we would measure the diameter of the tube and the length of the tube as we warmed them up. So that was how we did Charles law. But we don't need to do that anymore. So, all right, I gotta push along. Any, eudiometer tube, interesting. How are you gonna change the temperature of the whole tube? That thing's like, what is it, 50 centimeters long? So I mean, not to say you couldn't use a eudiometer tube. Those, you use the eudiometer tube for molar volume of the gas, that kind of thing. Not, I don't think it would be appropriate for this experiment. Unless you could figure out a way to, put the whole tube in some kind of water bath or something like that. So yeah, I did use them, but not for this kind of experiment. All right, Graham, Avogadro's Law and Order. Okay. So this was Dylan came up with the title for this experiment in the forensics book. Okay. So let me get a flask and I don't know if it matters if it's wet. But I don't need water baths for this one. This one is pressure and well, technically, it's pressure and number of molecules. But how do you do number of molecules? So what Avogadro proposed was that it could be volumes of gases, equal volumes of different gases, same temperature and pressure, equal number of particles. And it's like, really? I mean, I'm sure a lot of people were like, wait a minute, what are you talking about, Avogadro? And so let's try it. Okay. And I don't think I got any water in the flask. So I don't want water in the flask. Okay, and so I'm going to close that. Whoops, that's not closed. I'm going to get the syringe off. And what I will do, so this thing doesn't fall over, I'm going to clamp the flask to the stand just so I don't knock it over. So here's the deal. Got the pressure sensor hooked up. I'm going to inject 5 milliliter aliquots of gas into the flask, and I'm going to plot pressure against total volume. Okay, so that's the first thing to try. So new experiment. I don't need the temperature probe, but I guess it won't hurt anything to leave it connected. I don't really. By the way, if I don't need the temperature probe for the next two experiments, so because we're gonna assume the room is constant. If you're using graphical analysis and you don't need a probe or you want to add one later, down on the right here, you can click on the sensor setup. I don't need the temperature, so I can disconnect it because I really don't need. Oh, I lost them both. I probably shouldn't have fiddled with it, right, Melissa? It was all working good. I should have just left it alone. Plus, I'm running by Bluetooth, so you know how that could go. You guys with the Chromebooks, I know you're struggling with that. All right, so here's what I'm going to do. I'm going to use the syringe to get air first, and I'm going to put aliquots of air into this flask, and then I'm going to measure the pressure. Okay, so I'm going to do events with entry again, and oops, not type. So events with entry. The event is going to be volume of gas. Let's see, once again, it's gonna be total volume of gas, okay, that's in the flask. Okay, so, hey, Dylan, you got that number handy?
I had it. Hang on.
Actually, you know what? It won't matter because the volume's not, what was in there is not gonna matter. So I'm gonna say total added volume of flask, and then you won't need, you won't need to do that. It wouldn't make any difference. It's just a constant anyway. So here we go. So what I'm gonna do is I'm not gonna add anything to the flask. So I'm gonna hit collect, and let's get those meters up so we can see the pressure. So I'm gonna hit collect. Why is the pressure higher than room pressure? I'm gonna open the valve. I mean, we're in Beaverton, Oregon, should be a little lower than 101.3, but the fact that it was 103. So I opened it up, now I'm gonna close it again. Okay, and so I'm gonna keep that. What's the total volume that I added? Nothing, I didn't add anything. Okay, now I'm gonna add 5 milliliters. Open the valve, inject the gas, close the valve. Okay, wait till the pressure stabilizes. How much gas did I add? I added, total now is 5. Okay, let's take the plastic, take the syringe off, another 5. Inject, close the valve. Total add, wait till this is stabilized. Total added was 10. Let's do a couple more. So some point it'll definitely pop the stopper out. I don't want to do that. Okay, open the valve, in, close the valve, wait, keep. I've added 15. Let's go up to 20. I don't want to, try my luck here. You guys can try higher with your students if you want. Okay. Open the valve, flow, inject, close the valve. Oops. Make sure the valve's closed. That looks pretty good. Keep. Total is 20. All right, I'm going to stop. All right, look at that. Pressure, what's the relationship of pressure to the volume of a gas? Pretty linear. Okay. But what about other gas? Oh my gosh. I don't know, Melissa. The feng shui in here is perfect today. Look at that correlation coefficient.
Seriously.
Gee, and I'm going fast.
Yeah. Maybe that's the trick.
I guess. Okay, I'm gonna save this because I don't want to lose it. That's like so good. This one's what, Avogadro? All right, let me save that. All right. Now, go back to the presentation. This is where I used to do this with my students. Okay, let's go look at the graph. Delta P. Let's get statistics. So the pressure changed by 12.85. Let's call it. So I'll put that in for air. Oops, I can't do that when I'm showing the presentation. Okay, so sorry. I would put this on the board or have it up on the screen or something, and where it says air right here, you write in 12.85 kPa was the change in pressure when 20 milliliters was added. Now do a different gas. Now I would have the kids work out the molecular weights. This is all, of course, a red herring. But let's do carbon dioxide because I've got Alka-Seltzer here. 44 grams per mole. Air is around 28.97. Have the kids predict the value. Don't tell them too much. I promise you, they're going to put a higher number in here than 12.8. Unless the kid is super duper smart. If in their mind, if the molecular weight is higher, I mean, look at okay, don't hate me. I used to do Freon because you can balance the balloons. I mean, Freon's 131 or something like that. But even difluoroethane, that's the stuff that's in the sprayer that you put on the keyboards. So you can get these gases are relatively easy to guess. In your lab, you might have either butane or propane, so that would be one you could use. I'm gonna do carbon dioxide. Let's see. I don't know, man. Am I pushing the fates here? I might be. Okay. So here's my gas generator tube. Number 5 stopper with a 1 hole. Okay. So this does not come with the pressure sensor. So if you do use the number 5 2-hole, you'll have to figure out a way to block like maybe 2 valves or something like that. So I'm going to put some water in there it doesn't matter how much, I think in the lab, I wrote 10 milliliters. This one is in the forensics book. It's called Avogadro's Law and Order. Related to like rocket launches, the idea that you pump up the 2 liter bottle rockets and kids, the idea is kids didn't follow instructions. What? Kids didn't follow instructions? All you need is like a quarter of an Alka-Seltzer. Too much more than that, and it's going to blow the thing out. Leave the valve open. Carbon dioxide's heavier than air. It's going to push the air out of the flask. So it's going to be a full flask of carbon dioxide. Put another little bit in there. Okay. Doesn't take long. You wanted to test it, you could like try a wooden splint, a glowing splint, and you'd see that it would go out. So now close the valve. Let's capture. Okay, on this flask, I need the original flask. I'm going to open it up. Just had air in it. Go back to normal. Close the valve. Okay. Now let's get some CO2. Well, actually, first data point is 0, right? So let's get the first data point. Close these doodads so they're out of the way. Collect. Do you want to create a new data set? Yes, I do, because this is CO2 this time. And first data point is 0. So I'm not going to put anything in. All right, now open the valve. And oh man, this is just looking at me the wrong way. Here we go. And it should just push the valve out. There we go. And 5 milliliters. Okay, close the valve. Move quickly. Carbon dioxide is heavier than air, so maybe upside down isn't the best choice. And then inject CO2, 5 milliliters. Close the valve. Okay. Wait till the pressure stabilizes. Hit keep. I put in 5 milliliters of CO2. All right, let's go get some more CO2. So I'm going to go get another 5 milliliters. This, unfortunately, it's never where I want it to be. Here we go. Open the valve. Hopefully there's some pressure in there. There we go. Isn't that cool? The hand of God moving that up there. Okay, work quickly. Take that over, stick it on the other one, open the valve, close, inject the gas, close the valve, watch the pressure. Keep, how much did I put in? 10. All right, now let's go get some more. I don't know why, it's never in the right spot. All right, here we go. 5 more milliliters. All right, quick. Could turn it the other way, if you're worried about it leaking out or something. All right. Keep 15 milliliters, one more, just to be consistent with the last run. Avogadro's Law and Order. Yeah, the idea was that the kids, the parents wanted to sue the school because the kids got hurt by this rocket launch thing where they, they basically they pumped it up too much, and when they did that, it blew up. And so, why, the whole point of the experiment is to learn about Avogadro's law, but what I put in there, 20, okay. And so it's, but I had to make it forensicsy. Okay, let's see. What happens if I put the other one on top of this one? So I'm going to go here. What's the other one? Well, this one was CO2. So I renamed it. There's a little pencil right here that you can go and rename your data sets. Okay. Other nice thing is you can also play around with the colors. So that's pretty good. Let me turn them both on. Ooh, what the heck? They're nearly on top of each other. What was the pressure change for the CO2? Let me turn the air off temporarily. And let's look at the statistics for the CO2. 13.25. Now I was being a little bit quick on this one. How did just out of curiosity, what's the correlation coefficient for that since I was going so fast? Let's see. Yeah, not 0.989988. So two nines correlation. So I was going pretty quick there. But point being is, I promise you, kids are going to put a much larger number over here for the change in pressure. It's not. This is almost the same, right? The first one was 12 point. Well, let's go put it on there. If you turn them both on, it puts them both on the screen with different colors. So if you do the statistics, so the red one is, I think the last one, 13.26. The other one was 12.8. I promise you, if you're a little more careful than I was, they're going to be even closer together. So what are we proving here? Volume of a gas is directly proportional to the number of moles, and equal volumes of different gases at the same temperature and pressure have equal number of molecules. And it doesn't matter what the gas is. That's the one that kind of blows people a little bit away. Yeah, magnesium hydrochloric acid. Yeah, Craig, that's the molar volume one, that the uniometer tubes are great for. We have that, by the way, in one of our lab manuals too. All right, what do we got? 15 minutes is plenty of time to do Boyle's Law. Everyone has seen Boyle's Law, so before I do it, that one has a nice calculate column option in there. But before I do it, anyone have any questions or comments or concerns? Please let me know. Okay. Okay. Sorry, I don't have a lot of time. In class, I would wait at least a minute. But we're going to do Boyle's Law. And so Boyle's Law, my favorite Vernier experiment of the year. Why? Because you only need when you buy the gas pressure sensor, it comes with this little bag of goodies. By the way, don't put that out. If you put that out, those little ratchet clamps, they're the first thing that's going to disappear. And when your biology teacher wants to do the transpiration lab, they're not going to be happy. Just put out what they need. But when you're doing Boyle's Law, you only need one thing: the syringe. Well, technically two things: the syringe and the pressure sensor. That's it. So setting up the Boyle's Law lab is like the easiest thing in the whole wide world. Okay, let me save Avogadro here. We'll start a new experiment. Please don't hesitate to jump in and say, hey, News, what about the thing? Okay, to do this one, let me clear all this other junk out of the way so you're not distracted by it. So that and the syringe, and let me clean up a little of my water mess that I made. Okay. So what we're going to do is we're going to, once again, events with entry, pressure against volume. So we did volume against temperature. We did pressure against temperature. We did pressure against number of molecules or moles. And now we're going to do pressure against volume. And then we'll have all of PV equals nRT covered. So the issue here is time. Again, so we got to change that to events with entry. This time, the entry will be volume, because it's going to be the volume of the gas. It'll be the same number of molecules, but the volume of the gas. I'll leave it as the milliliters. Oh, I forgot to bring it. Dang it. Um, you'll see here in a second. So what I'm going to do is I'm going to put the syringe at 10 milliliters. I have a taken apart gas pressure sensor to help show you this next thing I'm about to do. So I'm going to start collecting data and, oops, get the meter up here. Whole Logger Pro guy, I used to love it. The meter just stayed up there all the time. Not that hard to turn it on. It's just, I want to grouse a little bit and commiserate with some of you folks. So anyway, let's see. Let's keep that point. And now here's the thing: the syringe is at 10 milliliters. But it turns out, and that's why, Dylan, I knew I was going to forget something. I have one of these taken apart so you can see the insides. And there's 0.8 milliliters of volume that there's a little, real teeny weeny little plastic tube that runs to the actual sensing module that's in here for pressure. So the volume is actually 10.8 of the gas right now. Okay. And if your students didn't put that in, you can always do a calculate column and fix it. I'm gonna push this down to 5 milliliters. These go direct pressure sensors, they, this is a real good one for 2 people. All right, I can relax now. 5.8. These go direct pressure sensors can go up to 4 atmospheres. So you could compress the heck out of this thing if you wanted to. I'm gonna go up to 20 milliliters. Hold it as steady as I can. And then 20.8. And I'm just gonna go down by twos. So 18. Once again, doing this pretty quick. So let's see how good my correlation coefficient comes out. 16. Doesn't really matter what order you do them in. I like doing, when I'm doing like a demo like this, I like doing it this way because if I pull it out, it kind of sucks itself in automatically. And I don't have to be quite as careful. 12.8. And 10 we already did. Let's do 8. The way with events with entry, you just keep going until you have all your points. And by the way, it's the same mode. What is this one? 6.8. It's the same mode that you use when you're titrating an acid base. Oh, did I make a mistake? Oh, that's good. Why is it good? Let me stop looking at it. Well, it's because in the Vernier land, when you're doing events with entry, any value that you put in, you can change. You can't change values that the sensor collected. So what is this weird thing over here? 0.8 and 129. And yeah, that one, that's definitely something weird going on there. Not 100% sure what. I don't think I entered it wrong. Oh, wait a minute. How can that be 12.8? 5.8, 8, 6.8. Oh, this one's 8.8. Yeah, so if I go in there and I just type in the value. So you can change values that you put in. You can't change values that the sensor collected. You're teaching, what level are you teaching? Ninth graders, pressure is inversely proportional. This is one of those fits that you might want to do that's not linear, right? You do a fit, but instead of choosing a linear fit, you try, let the kids figure it out, right? They could do power, they could do inverse, they could do, let them try it as quadratic, kind of, sort of, kind of. Here's power fit. Ooh, that looks pretty good. The inverse fit. It depends on the level of the students. I like the power fit because, we kind of sort of want to teach that it's, that X is raised to the -1 power. And so you can look at that and go, where's X? X is B, right? So -1, that's not too horribly bad with me doing it one-handed. Now, the other thing is you want to get a relationship between pressure and volume, and it's inversely proportional. So if we want to get a relationship of P is equal to some number times 1/V, what we need to do is do a calculated column. And so we have a lot of folks that don't know that you can do that. We can take the inverse of the volume and we can plot that. So we click on the 3 dots and we choose calculated column. We could, calculate this right in here. Do you have to do it this way? No, you could export the data to Excel or Sheets and you could do it that way. But just know that there's a fair amount built into graphical analysis, even the free version. Trying to think, I don't think there's anything I did today that you can't do, you need pro for. And so everything I did today was the free version. Oh, let's take a look at the inverse plot. So let's do P versus 1/V. Don't look too bad. Let's see. All right. Drum roll, correlation coefficient. Let's see. Here we go. Linear fit. 3 nines correlation. That's not horrible, you know. Yeah, thanks, Alyssa. It took me too long to figure that out. But yeah, thank you. Yeah, that's not horrible, right? Nice thing is when you're making a report with graphical analysis, you could have more than one graph up and have like the original plot at the top and have the inverse plot on the bottom. And then when the kids go to make a report, they could, take a screenshot is what I usually tell folks. But we do have some ways to export. I think turn off all the stuff you don't need and just take a screenshot. I think that's probably the best way. You can title the graphs and all that, but only got 5 minutes left, and we have to do a drawing. Can you slow a bit to explain the relationship, showing when inverting the axes? So what I did, Will, is I did a calculated column on the data table. And I apologize. I know I'm giving you the bum's rush here, but we only have an hour. But in the data table, what you do is you pick whatever variable that you want to do a calculation on. So I wanted to calculate on volume. So I clicked the three little dots and I had this option to create a calculated column that was using I'll call it 1/V because if I try to name it the same thing, graphical analysis will yell at me. And then what I did was I went down here and picked an expression, and it was this one A over X. X is the variables, A is constants. So when I pick that, it puts a value in of one by default, 1/volume. So that's how I got the calculation. So you'll get a copy of the video for this at some point, or you get a link to it at least. And so you can go back and take a look and see all these instructions. Go back to the here. All these instructions are in the shared folder. They're student experiment instructions right here. So here's the Boyle's Law experiment, and everything you saw me doing is right here under processing the data. So don't feel too. I know. I mean, it's like I got 4 gas laws in an hour. Now in your classroom, yeah, maybe we don't do that. But most of all the gas laws, you need a pressure sensor, maybe a temperature probe, and maybe some water baths. Kind of simple. Okay. Where's the presentation? Here we go. I put this in the shared folder. Um, every class had to show it to me. And then they got the Avogadro award. This one's nearest for Avogadro's number, but what's in there's an electrochem experiment for that. What's in the shared folder is a Google, I don't know what they call it, but you can modify it. You can take this, make a copy of it, and then you could change that to, best absolute zero or something like that. Is there a link to the files on Google? Yeah, it's hey Dylan, did you drop it in there again? Yeah, it's Kevin, look at that link that Dylan dropped in just before your message. And it's there. Melissa, did I miss anything?
Nope, I don't think so. I was just gonna help point out some of the links in the chat, but you already did that. So
Oh, I'm
let's
sorry.
get to that giveaway.
I got on a roll there, and you know how that goes with me and being on a roll. So Go Direct gas pressure sensor is the prize. Okay. Dylan, who won?
Yes, so I went ahead and entered everyone's name into a random name selector, and today's winner is Quentin K. Quentin or Quinton, I'm sorry, but I am going to email you, and I just need to get some shipping information, so keep an eye out for an email from someone with an @Vernier email address. If you don't see it pop up, check your spam. It'll be within the next 20-ish minutes.
Folks, don't hesitate to let us know if we can help. Melissa and I both taught, and we've done lots of presentations. And please don't. I'm so sad when I'm talking to a customer or reading a chat or an email. I spent 5 hours on this experiment. Oh, don't do that. let us know so we can jump in and help you. Okay? So nice to see you all tonight. Dylan, are we done?
That's it. Go ahead and give us feedback if you can. And we are so grateful for your time and energy. We've got some really exciting forensic webinars coming up this summer. So stay tuned and congratulations to everyone who is just nearing the end of their school year.
Oh, yeah, absolutely. All right, folks, have a good evening and good luck for the rest of the school year.
Bye, everyone.
Bye.